A circuit with a couple of bulbs connected to a battery, and I ask you to measure the potential difference across, say, this bulb. How will you do it? You might look at me in a funny way and say, that's so obvious, Mahesh, I'm just going to hook up a voltmeter across it. Okay, that's probably what I would do as well. But here's a problem with the voltmeter. The moment you attach it across, it's going to start drawing some current. And when you do that, the current in the circuit is going to change. We have disturbed the circuit. And so the voltage has also changed a little bit. And therefore the voltage that you're measuring right now is not exactly the voltage that was before you attached the voltmeter. And so our reading is not very accurate. Now, of course, in most of the circuits, this current drawn is extremely small. And so we can neglect it. However, if you want an extremely accurate measurement of the potential difference, then we cannot neglect it. And so this brings us to the main question of the video. How do you measure voltage between any 2 points without drawing any current from the circuit? And you may have probably guessed from the title of the video, we're going to do that using a potentiometer. Now, when I was introduced to potentiometers, I always got confused because there were so many circuits, primary, secondary, and so many things were happening. And so what I want to do over here is start logically, not with the circuit. So we'll start with the logic, understand the principle behind the potentiometer, and then we'll get to the circuits and all the details. All right, so coming back to our voltmeter, if we wanted to make sure there is no current drawn over here, then the only way to do that is to have incredibly high infinite resistance, and that's practically not possible. And so we need to move away from voltmeter. Here's how I like to think about the principle of potentiometer. I'm going to first connect a battery across the bulb through a galvanometer. At first, this sounds ridiculous. You may be wondering, why are we attaching a battery? Isn't that going to disturb the circuit as well? And that's not even a measuring device. And how are you going to measure voltage using a galvanometer? So many questions, right? And you're right, it sounds ridiculous, but it'll make sense in a second. So notice that this is not any normal battery. It's a battery whose voltage can be changed. So imagine there's a knob over here with which I can increase the voltage from, say, 0 to 5 volts. So the voltage of this battery can change. So what, you may be thinking, right? Well, let's dig into this now. So let's think about the potential difference. Here we have some potential difference, and this is the positive potential, higher voltage because it's connected to the positive of the battery. And here we have some lower voltage. Let's call that lower voltage as 0 volt, just to keep things simple. And so all I have to do now to figure out is what is this value. If this value is say +2, then I know the potential difference is 2 volt and I'm done. Okay, now coming back to our battery, right now this, since is directly connected to the negative terminal of my battery, and we can neglect the resistance of this wire, we can say this is also at 0 volt. And let's say my battery voltage currently is also close to 0. That means this is also pretty much 0. Right now we don't have any potential difference over here. So in this situation, there is some voltage here and there is 0 voltage over here. And so we would expect some current to flow over here, right? And so in this situation, the galvanometer will show me some deflection. So if I look at the galvanometer, there it is. It is showing some deflection. And of course, right now the circuit is disturbed and this is not the position I'm intending for. However, let's say I turn this knob a little bit and now push this to 1 volt. So I push this to 1 volt. What do you think is going to happen? Now, since I've increased this voltage, the potential difference between these 2 points has reduced, right? Does that make sense? It has reduced, and as a result, the current flowing through the galvanometer also reduces. And I can see that in the deflection of my galvanometer. And so you see where I'm going with this? As I turn up this voltage, the galvanometer deflection becomes smaller, and at one point, it becomes 0. So right now, my voltage is at 3 volt, as you can see in the bar over here, and the galvanometer deflection is 0, which means how much voltage should be over here? Ooh, the voltage over here must also be 3 volts. Because if it was any other number, there would have been a potential difference across the galvanometer and current would be flowing. So the very fact that there is no deflection means the voltage over here must also be 3 volts. And notice, since there is no current flowing through the battery, the galvanometer right now, I am not disturbing the circuit. I have measured the voltage across these 2 points without drawing any current. Ta-da! That, my dear friend, is the principle of a potentiometer. You put a voltage source across with a galvanometer and you keep increasing that voltage source. Eventually, when the galvanometer deflection becomes 0, we know the voltage over here must be exactly equal to the voltage that we are measuring, and that's how you calculate the potential difference. Okay, you now understand the core of the potentiometer, the principle of the potentiometer. All we need to understand now is how to convert this into something more practical. You see, batteries with whose voltage can be changed, these are hard to come by. So the next question we want to have to make it more practical is, how do you achieve this by using a regular battery whose voltage you can't change? How do you calculate the voltage now? Now what we will do is, instead of directly connecting it to our circuit, we will connect this battery to a wire. Why are we doing this? To be able to vary the voltage just like before, but now with the wire. Here's how it works. See, if I were to connect these 2 points, then the voltage that I'm providing now is 9 volts, and I can't change that, right? But what if I were to connect between this point and the midpoint of the wire? Then how much voltage would that be I'll be providing over there? Ooh, that would be just half of 9 volt. Because I can now say that this part of the wire and this part of the wire are identical and they have the same resistance, and so the voltage should get divided equally. And therefore between the midpoint, I would get only 4.5 volt. What if I were to connect this and over here? I would get even smaller voltage. Ooh, so you notice if I connect this over here, but from here, if I were to slide across this wire, the amount of voltage I provide will keep increasing, just like what I did over here. And then I can use a galvanometer, find the balancing point and figure out at what voltage I would get 0. So just like before, we're going to connect with a galvanometer, but over here, I'm going to use a slider. And say right now, the voltage that I'm providing is pretty small compared to the actual voltage, let's say, and therefore there is some galvanometer deflection, and so there's a current running. But as I move the slider to the right, the voltage that I'm providing increases, and just like before, the galvanometer deflection starts decreasing. My voltage is coming closer to the measured voltage, the voltage I'm measuring. It's coming closer, and right now, here we go. Right now, the galvanometer deflection is 0, meaning the voltage over here is exactly equal to the voltage over here. So all I have to figure out now is what is the voltage across this part of the wire. And there you have it. This is your potentiometer circuit. We usually call this as the primary circuit, this as the secondary circuit. But you get the idea, right? It's very similar to what we did over here. But of course, here, directly the voltage calculation was available to us. Over here, how do we calculate the voltage? That's the question that we're going to ask now. How do I know how much the voltage across this part is? So this has nothing to do with the potentiometer. Now we just have to do some basic, electricity calculation. So here's how we'll do it. I know that this particular length of the wire, let's say this length of the wire was, this wire was, I don't know, maybe 3 meters long. Okay? And let's say that we found the galvanometer deflection to be 0 at 2 meters. So we'll call this as the balancing length, or the null point, because current is null. And this is at 2 meters, let's say. The question is, what is the voltage across these 2 points? Let's call it as point A and point B. I want you to take a shot at this, because there's nothing to do with voltmeter. Think about this. The entire 3-meter wire has 9 volts across it. So the question is, how much voltage is across the 2-meter wire? Can you give this a shot? Pause the video and try. All right, here's how I would do it. I know that 3 meters of wire has 9 volts. So per meter, how much voltage do I get? So that number, the voltage per meter, is often denoted by phi. And that number for us is going to be 9 divided by 3. So 9 volt divided by 3, and that's going to be 3 volt per meter. So I know every meter of this wire has 3 volts. And also it's important to understand it's a linear thing, because see, every meter of wire is identical, right? The whole wire is uniform, and that's important. The wire is, the area of cross section is uniform over there. And because of that, the voltage across each meter must be exactly the same. And so it's a linear relationship. And so now I know that every meter has 3 volts of potential drop across it. So how much does 2 meters have? I just multiply that. So the voltage between A and B, that's what I'm interested in. The voltage that I'm measuring, this is also A and B now. Because there is no current flowing, both are at the same voltage, remember? And so VAB should be equal to 3 into 2. So that is 6 volt. And so in general, whatever voltage we are measuring is going to be the voltage per meter, which is phi, times the balancing length. And there you have it. This is how you calculate the voltage through a potentiometer. And I don't want you to remember this formula or anything. This comes, if you understand, the logic behind this, then this formula can be understood from first principles. And of course, now in actual practical circuits, things get a little bit more complicated because there are additional resistors involved in our primary circuit. We don't want to directly connect the battery to the wire. And so how does that change things? The only thing it changes is the voltage across this wire, the primary wire. Right now it's 9, but if you put a resistor over there, that voltage will change. And you can calculate that using maybe Kirchhoff's laws or Ohm's law. But once you do that, the main thing we need to calculate is how much potential difference you have per meter, right? And there's a technical term, we usually call this the potential gradient. Gradient means how much things are changing per meter. And so if you know this number for any potentiometer, you can just multiply it by the balancing length and you get the voltage measured. Final couple of things I want to mention before we wrap up is, one is how do you make this potentiometer even more accurate? One way to do that is to make it more sensitive. As I move the slider across, let's say I want to make that galvanometer deflection happen very slowly, so that when it comes to exactly 0, I stop it, right? In order to do that, we need to make it more sensitive. And one of the ways of doing that is by increasing the length of the wire. Imagine this wire was not 3 meters, but say 10 meters long. The voltage across this is still 9 volts, meaning the potential gradient would have now reduced, right? This big number becomes 10 meters, so potential gradient will be smaller. And so as I move my slider across, the galvanometer deflection would slowly change, and I would be able to precisely find the balancing point. And it's for that reason the potentiometers that you find in your labs will have so many windings of the wires. The whole idea is to increase the length of the wire as much as possible. Finally, one last interesting question would be, when you're conducting this experiment, let's say you don't find the balancing length at all. It doesn't matter where you go, your galvanometer doesn't show 0 at all until the end. What could that mean? Can you think about that? There are two possible scenarios in which that can happen. All right, one scenario is if the voltage that you're measuring is larger than the entire voltage across the wire. I mean, think about it. If this voltage was, let's say, 10 volts, then it doesn't matter where I go, I will never be able to balance it out, right? And so it's important that the voltage that you're measuring has to be smaller than the voltage of the wire. Or you can just say, to be safe, has to be smaller than your battery voltage in your primary circuit. Okay, but there's another possibility. Even if the voltage is smaller, let's say you took care of that, there is another possibility in which the galvanometer deflection could never ever become 0. And I want you to think about under what circumstances that could happen. Stay curious.